Welcome to Marine Tech Talk, a podcast about how Teledyne Marine's innovative technologies are enabling scientific discoveries and commercial tasks in the world's oceans and waterways. On this episode, we hear from Dr. Alexander Forrest, an associate professor for the Environmental Robotics Laboratory in the Department of Civil Engineering at the University of California, Davis. Dr. Forrest's group focuses on applying autonomous robotic systems, like AUVs and gliders, outfitted with seafloor mapping and water column measurement sensors, to examine how localized topography influences water flow in lakes and nearshore coastal zones in the ocean. Here's Dr. Alexander Forrest with the host of Marine Tech Talk, Melissa Rossi.
So, Alex, can you tell me a little bit about your program at UC Davis?
Sure. I'm in civil engineering and I'm in water resources, and my group is the Environmental Robotics Lab, and we're trying to use robots and underwater robots specifically to look at problems in environmental fluid mechanics. Mm-hmm. And what that means is basically the application of fluid flow to environmental problems. So whether or not it's ongoing work in Lake Tahoe on its clarity, to algal outbreaks in Clear Lake, to applications in both poles, we're trying to use tools in novel and interesting ways to come up with new applications. And so we sort of have a growing team that go out and look at various problems, and the team involves technicians and students. And so we then put them into situations like heading down to Antarctica.
That's a situation.
That's a situation. Well, actually, it's quite stressful for me as the supervisor on that, because a lot of these are student-led.
Oh.
And they've so far done an amazing job every time they go out.
That's fantastic. When you went out last time, you talked about a team. Your team, when you went out in 2017, was even bigger than your own group. You had several other organizations. Who did join you on that expedition?
A lot of this was being driven by the Korean Polar Research Institute, which is COPRI for short. And so the PI, so the principal investigator there, his vision is to bring together a bunch of different teams with different elements to be able to look at a system in its entirety, from both airborne measurements to underwater measurements to on surface, on the glacier, making observation stations in meteorology, and linking all those things together. So we have partners from NOAA, we have partners from New Zealand, Australia. Now we have about 12 different research institutes involved in this larger, then it was called Lioness. So Lioness was this broader package of which our team from UC Davis was running the smaller underwater robotics side of things. At that point, what we were looking for was evidence of flow coming out of subglacial channels. And you may ask what a subglacial channel is. Basically what it is, if you can imagine how we picture an iceberg or an ice shelf as basically a flat bottom. And so as the bottom melts, that water is released and comes out into the ocean. Now, as ice shelf starts to melt more, basically it starts eroding the bottom and starts forming an inverted river channel, essentially. And then the water that's flowing through there starts picking up speed and gets channelized and starts eroding the structure of the ice shelf itself.
So were you looking at or trying to determine the rate that was happening? And what was, or just to understand the dynamics, the fluid dynamics there?
We were trying to understand the fluid dynamics, how fast the flow was, what temperature it was, because by knowing those characteristics, we can start inferring how much of that is melt.
Okay.
So how much of that is melting and where that water could be potentially coming from. In 2017, we were very successful in using the glider to basically fly parallel to the front of where the ice shelf had broken off, and got evidence that there's basically a plume of water coming out from underneath the ice shelf that it's referred to as supercooled or super cool.
Super cool water.
Super cool, 2 words, versus super cooled, 1 word. Basically what it means is that ice hasn't formed in it yet, even though it's below the temperature of freezing. Because in Antarctica, the water is so clear that there's not enough particles in the water for ice to actually start forming ice crystals.
That's really interesting. That's something I had no idea, that you needed those particles. So what type of sensors were you using on the glider to do that work in front of the iceberg?
Well, ice shelf.
Right, ice shelf.
Ice shelf. Iceberg comes later on when they break off.
Okay.
At that time, we're using pretty much a base vehicle, what's referred to as a CTD, so conductivity, temperature, and depth. So that measures ocean pressure, ocean temperature, ocean salinity. And then we also had a eco-puck, so it measures chlorophyll and turbidity. And so we were also able to discern some signals there in terms of plumes coming out. And then also oxygen. So looking at all the environmental characteristics of this water that's potentially terrestrial in origin, because it's coming down as the glacier feeds into the ice shelf and then melts and then comes into the ocean. So it has a different signal than the ocean water. And so we're trying to understand as a broader group how fast these ice shelves are melting. Because the reality is ice shelves are melting at an unprecedented rate in both the Arctic and the Antarctic. And we're trying to understand and quantify what is the rate that these things are melting.
And the other researchers were also looking at different ways at that same problem, or were they all doing different types of research?
All different types of research feeding into the same problem.
Okay.
So we can estimate heat flux, so basically how much heat is coming off through the water at the water-ice interface. But the glacier is also losing heat through the upper boundary into the atmosphere. So we need to quantify that as well.
So some group was doing that, I presume.
Some group was doing that.
Okay.
Some group was measuring annual measurements of ice thickness. Another group was doing measurements of the degree of cracking. Another group was doing hydroacoustics, looking at the flexure of the ice sheet itself. So it's a very broad group.
I would say that principal investigator, it was at COPRI,
Yes.
is a brave person and a very, very organized person to bring that many groups together to do that level of research. The coordination must be amazing to bring all those teams together, I presume at the same time or roughly the same time?
Roughly the same time.
Roughly the same time, to bring all of those groups together from, I presume, also all over the world. I mean, you've got a group from Korea, you're here in the US.
Other colleagues in New Zealand, in Australia, in Germany. So yeah, it's all across the world that we sort of partnered together to work on this.
That is a massive coordination project.
Indeed it is.
And so then you did it again this year?
Yep. So 2 years after the first deployment, we sent a team back. One student, Jasmine McInerney, was the key flight pilot. And then we also had another student, Drew Friedrichs, go down, who was doing work on microstructure, which was really the key question this time. So what microstructure is a measure of turbulence, which gives you an idea of how energetic the system is. So how quickly energy is being dissipated from the system. And a simple way to think about that is basically stirring milk into a cup of coffee. You stir it quickly and you watch the milk quickly sort of dissipate through your cup of coffee. Yeah. That's a highly energetic system. Okay. And it's getting rid of the energy quickly. So in the context of polar oceanography, it's getting rid of the heat quickly. So if you have a highly energetic system, it's advecting heat away, so then more heat is going to be lost from the ice surface to make up for the heat. So it creates a gradient and advects the heat away. So we had a hypothesis that this plume of water was going to be extremely turbulent one with lots of energetics transporting water and heat away from the system.
And is that what you found?
Well, before we even get there, so what we ended up doing was using a glider and strapping a microstructure probe.
Microrider?
Microrider.
Right.
And what this is a sensor that can measure very rapid fluctuations in temperature and shear. And from that, we can infer the energetics of the system. Okay. What we ended up finding was, if you can imagine, I'm waving my hands around here, but the water itself is coming out in a plume about 300 feet thick. As that comes out into the water column, we were sort of envisioning this entire 300-foot band as being quite energetic.
Wow.
It's a big band.
It's a big band.
We are in a large, so about 3,000 feet of water, and so there's this 300-foot band that's moving through the water column. And we ended up flying our glider about 3 miles underneath the ice sheet, sort of straight up into this flow. And then turning around and coming back out.
And that was not something you did before, right? Because
No.
on the last mission out to the Western Russia and out to the Nansen Ice Shelf, you flew it just in front
Yes.
of the ice shelf, correct? Not
Correct.
underneath it.
So this was a first for us, going underneath of the glider. And so that was a stressful 24 hours because we had no communications during that time. So it's basically comms blackout for 24 hours.
Wow.
We also strapped this microstructure probe on, and that hadn't been done before either.
Underneath the ice?
It's been done a couple of times with different types of vehicles, but with this setup, with the glider, it hadn't been attempted before. And we managed to find the band where this plume was coming out and managed to follow it all the way up. Three miles in, it goes another 30 miles back to the grounding line. We didn't do that. We weren't quite that brave. Or stupid, depending on. So as it went in and then came back out, the results that we found was that the system is very energetic at the boundaries of the plume, but the core of the plume was actually quite quiet, which was a bit non-intuitive for us. We were kind of expecting the opposite.
I would have thought the other.
Yeah. So basically what that means is where this plume is interacting with either water or the ice, it's quite energetic at the boundary. But the core is actually just sort of moving the water out. So we're currently in the process of trying to analyze this data and try to make sense of the data. But it's some pretty novel, exciting findings, and helps us sort of better understand these large, complex ice sheets and ice shelves as they're going through unprecedented melting.
Did you have any unexpected challenges while you were out there running the vehicles?
Well, yes. Polar oceanography in general is always a challenge. So before we ran underneath the ice, we wanted to find this plume again. And so we actually ran a run up and down, 40 kilometers up and then 40 kilometers back down the ice sheet to find it. And after that first mission, they brought it back to change the batteries and do some work. And during the recovery, they actually broke the tail fin.
Oh.
They ended up basically making a new tail fin out of epoxy and some pieces of plastic they found in the shop.
Because it's not like you can go to your local store out there,
Exactly.
right? Or get a quick FedEx delivery in.
Exactly.
Oh.
And so they jury-rigged something before sending it on this never-tried 24-hour mission.
No wonder you were holding your breath.
I was definitely holding my breath, particularly since I was sitting back in Davis. And this was like it was basically New Year's Day that they were sending it off.
Happy New Year.
Happy New Year's.
Happy New Year.
And then it was funny because they get these communication blackout times on the ship. And so they had actually gone off to do other science while the vehicle was underneath. And where they had moved to, they had no comms. And so when it came back to the surface, it actually popped to the surface. And myself sitting back in Davis was the first one that was talking to it.
Oh, wow.
And so I was like, it's on the surface, it's on the surface. And I'm trying to reach them and they didn't.
Alert.
Well, and I couldn't do anything. And it took them another 3 hours before they came back in communications to actually do a pickup. So I had actually been holding it on the surface remotely from Davis.
I was going to say, did you send it a message and said, hang on, buddy?
Yeah, pretty much.
The team's coming.
And so that was definitely some excitement there, for
Yeah,
sure.
for sure. Yeah. So just out of curiosity, because I'm thinking about all of this equipment, how big is that shipment when you go out there? I mean, is it, just the glider and a few pieces of equipment, or are you guys shipping like tons of equipment? When you're
No,
going?
I mean, from our perspective, we try to pare it down as much as possible.
Okay.
But in terms of like the ship logistics, so generally they'll be on the order of 40 scientists on board.
Okay.
And so each science group is bringing in their own package. So we basically deal directly with an importer who he basically convenes all of the gear in New Zealand.
Okay.
And then the ship shows up and everything gets packed on the ship and then the scientists arrive afterwards.
So if you have 40 scientists on that ship, then it must be obviously a research vessel. There must be labs and things on the inside for everybody to be able to do their work while either their equipment's in the water or where they need to process the data afterwards and look at it.
There are multiple labs. There's electronics labs, there's chemical labs, there's wet benches, there's dry benches. So it's always interesting doing this type of work at sea when you're sort of rolling around in a 10-foot swell and you're trying to do this work on a
I know.
bench.
I mean, it's not glamorous.
No.
That must be an amazing experience, though, to be with all of those different researchers, which I presume by this time, if some of them are the same, you've gotten to know them over time.
Oh, definitely.
But I remember you were telling me recently about having an experience eating a lot of Korean food on that particular vessel,
yes.
right?
I got really used to kimchi.
Oh, my favorite. My family's Korean, or at least half my family is Korean, so it's one of my favorites. Must be really good for you, fermented foods.
It's fantastic. And talking food, I have a bit of a nut allergy, and so kimchi was my de facto. Every time the food got a little too experimental for me, I knew kimchi was always safe.
Have rice and kimchi, it's all good.
Well, kimchi soup, rice and kimchi.
Wow, kimchi soup too, you're better than I am, okay. Yeah. So, for the conclusion of your journey on this last mission, are you planning another? What happens next?
Well, so a lot of this is actually linked to work we're doing in the Arctic as well. So we have another field site up of northern Ellesmere Island, which is about 83 north, and in Milne Fjord, and where there's another ice sheet, but in a much further state of, I won't say collapse, but it's much more deteriorated than the big ice sheets or ice shelves that you see down in Antarctica. And so one of the students that was down on the Antarctica trip, his other field site is on Ellesmere Island. And so he's been going there for the last 3 years, instrumenting the ice sheet, and then looking farther back inside the fjord, and trying to understand this flux of heat coming off the land and going through the ice shelf itself.
So is he using autonomous vehicles there, or is he using other equipment for that?
So
research?
that's a lot of mooring work.
Okay.
So ADCPs and thermistors and CTDs and all classical oceanography work. What we're trying to get to is, now we've sort of proven what we can do with autonomous vehicles down south, is to try to transport that back up north. And so to be able to do a comparison study between ice shelves in different states of existence, basically. I don't want to say deterioration, because some are still in reasonable shape, while others are deteriorating faster. And so the future direction for us is to continue sort of developing this comparison sites between the two poles, as well as pushing more and more to coordinated robotics. Because in this case, we had one glider. In 2017, we had one glider, one AUV. But what we'd really like to get to is a point where we have ongoing monitoring of these systems that are fragile, that are very susceptible to climate change, and that we're able to monitor them in an ongoing fashion. And so having multiple vehicles, and whether or not that's gliders or AUVs or moorings or what have you, we need a suite of tools to go out and quantify them.
Do all of those tools exist now, or are you still hoping for new developments, waiting for certain equipment to be developed? Or is it more a matter of procuring the equipment to expand what you're doing?
All of the above. If you had an infinite supply of money, which of course none of us do, you could just...
Unfortunately.
You could go out and buy the state-of-the-art now and make these measurements. But then the technology will change. It's incredible how far the technology has come in the last 10 years.
Right.
And so we have to continuously update, and as we update, things change and evolve. But at the same time, we also have to drive the need back into the vehicle manufacturers and the sensor manufacturers. So part of my work is through the Tahoe Environmental Research Center, based up in Lake Tahoe, where we do a lot of testing and development of protocols and development of detection using new sensors, and trying to use the glider and new behaviors, and try to test all these things so that when the team goes to the field every couple of years, that they have the skill set they need to actually do the work.
Yeah, and that's really important to us as manufacturers as well, to get feedback from the field, because we can manufacture the equipment, we certainly test it in the water, but we can't put it through all the paces, we can't put it in the same conditions that our customers might. And so, getting that feedback is essential for us, either to correct issues or to develop new sensors or new ways to do things, or sometimes it's to make things smaller. So that feedback's really crucial to us. I know that we have the first case study that we did with you, which we titled Studying Ice Shelves in the Western Ross Sea. That is available to any of the listeners on the Teledyne Marine website. Is there some place that they can find out information about your more recent journey?
That's a good question. I'm not sure if we actually have it written up anywhere yet. We've done a couple of small news releases that's available through the UC Davis website.
Okay.
And we also post the articles through the Tahoe Environmental Research Center, where we base a lot of our work, but we haven't actually done any sort of formal write-up yet.
Okay.
And that's where it's on my to-do list. I just haven't got there yet.
I know, because you have nothing to do,
No,
right?
absolutely nothing.
Absolutely nothing to do. If they want to find out more about your programs at UC Davis, if they want to find out more about the research you're doing, where would they find that information?
So on the civil engineering webpage.
Okay.
So the civil engineering webpage for UC Davis, as well as the webpage for the Tahoe Environmental Research Center, and just Googling both of those will quickly take them there.
And I know you're pretty good about tweeting stuff out while you're out on missions and projects. Where would they follow you there?
Our glider itself tweets, and that's actually the students that manage the glider account. So that's at Stormy Glider.
Okay, great.
So
is that the name of your glider?
So
does your glider have a name?
So the glider's name is the Storm Petrel.
Oh, okay. And where did that come from?
Its first trip, so its maiden voyage was down to Antarctica, and it was the first bird that we saw on our trip down there on the ship. And the Storm Petrel is called the Wilson's Petrel, and it actually migrates from pole to pole.
Wow.
And I really like that idea for this particular.
It seems perfect.
But my students renamed it Stormy.
Everybody likes a quick, short name.
Yeah.
That's good.
So.
Oh, that's great. Thanks for that information. I appreciate it. I know that many of our customers like to name their vehicles, the gliders, the AUVs, so everybody's got a good name. That's great. So our listeners should follow Alex and his team and keep abreast of what's going on next. You're doing great work. Thank you.
Right. Thanks so much.
Thanks for listening to the Marine Tech Talk podcast. If you have any questions or comments about this show, you can email host Melissa Rossi at marinetechtalk@teledyne.com. If you like this podcast, please make sure to subscribe on Apple Podcasts or wherever you're hearing this show. That way, you'll never miss an episode. Thanks for listening, and we'll see you again next time.